Okay, hello everyone. So in this video, we're going to be going through an exercise where we want to show that a language is regular. In this case, the language we want to show is regular is the following: the language um, over the alphabet AB, where the strings in this language are of even length and don't contain AB as a substring. So, for instance, something like um, let's see, BAA, BAAA. This is in the language, right? Why is this in the language? Because it has length 4 and it does not contain the substring AB, right? So AB is nowhere to be found. The string W2, which let's see, is ABAA, even though the length of W2 is 4, AB is a substring of W2, and so therefore uh, W2 is not an L. And so and obviously, of course, like if the string is just of odd length, then it's also not going to be an L. Okay, so you might sort of already be looking at the string and thinking, okay, let me start with the start state, and then uh, I need to sort of defend against AB as a substring, but also ensure that I have a string of even length. That's going to get a bit tricky, especially if like this restriction becomes more complicated. So maybe you don't want the substring A, B, A, B, and you also want it to be divisible by 7 rather than 2. So things start to get tricky. And so the idea is that we can kind of simplify or break this language down into subparts. So instead, one thing we could do is directly create an FA or a regular expression. Um, maybe an FA, maybe like an NFA, this wouldn't be that bad. But like I said, if you started getting something like pretty sophisticated, like, divisible by 7 and does not contain the substring, then even an NFA, it's going to get you only so far. Regular expressions, likewise, not contain ABBA, something like that. That's going to be tough in a regular expression. So instead of taking this path, which is possible but maybe a bit tricky, I'm going to break the language down into simpler parts and leverage the closure properties. Closure. Closure properties. Closure, which is also the name of a programming language. If you're taking computational linguistics, you know all about closure. Well, if you're taking that class at McGill, at least. Um, okay, so break the language down into simpler parts. How are we going to do this? Well, it looks like we can do this because we have like an and a not here, right? So really, this is saying something like condition P, right? So P has to be true, and if contain AB as a substring is Q, then it's like not Q has to be true, right? So if we think about set theory a little bit, if I have something like X such that P and not Q, then actually this is sort of equivalent to something like X such that X is in P, intersect with the set X such that, or sorry, such that P intersect with the set, all the set that contains elements, where those elements satisfy not Q. And then I can sort of simplify this a bit further where I can say, well, actually, this is X such that P intersect with uh, X such that Q kind of complement. And from set theory, you might remember that A intersect B complement is sort of almost by definition the same as A different B, right? So really what's going on is we have something like this, essentially. So we can rewrite the language L here. We can rewrite the language L here as strings over AB such that they're of even length, which is a bit of an easier DFA to make. Different, right? So, and they're not, right? They're not from the set um, or the language of strings where W does contain AB as a substring. Okay, well, this is also the same as something like, um, let's just convert the like difference to like the intersect with the complement. Then I have, if this is L1, if this is L2, then I have something like L is equal to L1 uh, intersect L2 complement. And I know that regular languages are closed under the complement because you just swap the accept states with non-accept states and the non-accept states with accept states. And I know that regular languages are closed under the intersection because you can do like the product construction. So that means that instead of designing a DFA for all of this thing directly, thus showing that L is regular, what I can also do is I can show that L1 is regular and L2 is regular, and the conclusion that L is regular will follow from the closure properties. So, and you're going to see in a second that that's quite easier to do because, for instance, a DFA for L1, well, that's when I want to create a DFA where I accept strings if they're of even length. So this is just a DFA that kind of flips back and forth between um, the length is even, which is going to be the start state, and the length is odd, which is going to be the the other state, right? So the flip of the start state. And I want to accept strings if they have an even length, so I'm going to make the start state an accept state. So that makes it, that sort of tells me or sort of shows that L1 is regular. Then I can make a DFA for L2. So I need to make a DFA for L2. So actually, I could actually just make an NFA, which might be even simpler. NFA for L2. Um, where the NFA could be something like, you're looping, and then if you find AB, then you go to your accept state, then you accept, right? So this could be one way to do it. You could also design a regular expression, which is also not that bad. And just for fun, what would the DFA be? It's probably not that bad. So you want to hard code A and then B. If you have that sort of, if you recognize at some point that hard coded path, then you're always happy, you always accept. Um, if you're at the start state and you're reading B's, then you're still awaiting the A. That's going to be maybe the beginning of this AB. If you're in this intermediate state, so the state here, and you're seeing an A, well, there's still hope, right? If you're seeing an A, then you shouldn't go back, right? You shouldn't go back because the last thing you've seen is an A. So if you see a B, then you're immediately done, right? So if you see an A, then you're immediately done. Right, and so then I have a DFA for L1, and I have an NFA, also a regular expression, also a DFA for L2, which shows that L2 is regular, and so that means that L2 complement is regular, and so L1 intersect L2 complement is which is L, has to be regular by the closure properties. So since L1 and L2 are reg, and reg are closed. So by reg, I just mean the family of regular languages are closed under intersection and complement. This implies, and of course, and L is equal to L1 intersect L2 complement. And therefore, we have that L is reg. Okay, and just sort of FYI, what would the so and this kind of concludes the you could have sort of concluded here and full marks if that was the question. Just out of curiosity, what would the DFA have actually looked like? So we can actually construct it from this DFA and the complement of this DFA, right? So let's using the product construction. So let's do that just for fun, right? So DFA for L1, and then this is the DFA. This is the DFA for L2. And so then the DFA for L2 complement, right? Because what I need to do is the product construction of L1, L2 complement is, like I said, you sort of flip accept and non-accept states. Okay, and let's call this S0, S1, S2. And let's call this Q0, Q1. Okay, so now let's do the product construction. So the product construction, I take every possible pairing of states from my machine, let's call this M1, and my machine, let's call this M2. This was a bit too long. So let's see. So I'm going to have Q0, S0, Q0. I'm trying to think, is there like a, there probably is. Q0, S1, Q0, S2, Q1, S0, Q1, S1, and Q1, S2. Okay, so now these are my states. So remember product construction, the start state is the state that has as a pair, right? The start state of M1 with the start state of M2, right? And notice I'm doing the product construction of like M1 with M2 because it was L1 intersect L2 complement, but because intersection is commutative, I could have also done M2 intersect M1 because that's the same, because these two languages are the same, because intersection is commutative. But I'm just doing this order just because it's the one that's sort of present here. So this is going to be my start state because it contains the start state of both M1 and M2. The accept states, so the accept states are going to be the sort of states that contain as pairs accept states from M1 and then accept states from M2. So that's going to be, Q0 with S0 and Q0 with S1. So that's going to be Q0 with S0 and Q0 with S1. And now it becomes slightly tricky. Okay, let's see if we can do the transitions. So if I'm at Q0 and I'm at S0 and I read a B, then I'm going to go to Q1 S0. So I'm going to go to Q1 S0 with the B. If I read an A, then I'm going to go to Q1 S1. So with an A, I'm going to go to Q1 S1. Okay, so now what about Q0 S1? So if I'm at Q0 and I read an A, I go to Q1. So it's always, I think the nice thing is that you're always going to do this, right? You just have to find where you're going to go here. So From Q0, reading either A or B, you go to Q1. Now from S1, reading an A, you go to Q1, S1, yes. And then from S1 reading a B, you go to S2. So because from Q0 reading a B, you go to Q1, then together you go to Q1, S2. And then Q0, S2, well, S2 reading A or B, you go to S2. And then Q0 reading A or B, you go to Q1. So then we have AB here. So I have a feeling that this is going to be a dead state. Okay, so now I'm at Q1 S0. Now what's probably going to happen is that I'm going to go back here, right? Because this is sort of the row for Q0s. So if I'm at Q1 and I read either A or B, then I'm going to go back to the rows for Q0s. So let's see, Q1, reading A or B. I go back to Q0. Now the question is, what about S naught? So S naught, reading a B, I stay at S naught. So that means that I have something like this here. And then if I have an A, then I'm going to go to S1. Okay, nice. Then from Q1, S1, from S1, if I have an A, I'm going to go back to I'm going to stay at S1, but I'm going to go to Q naught. If I have a B, that means that if I have a B at S1, then I go to S2 in the Q naught row. And then if I'm at Q1, S2, right, yeah, so this is kind of like a dead state. If I'm at Q1, S2, if I read A or B, I go back to Q0 from Q1, and for S2, I also go to S2. Okay, so this is not like super clear. I can like just quickly merge these guys because I know that they're sort of both dead states. So let's see. Copy. So reading a B, I have a dead state, which makes sense. Why does that make sense? Because if I'm here or here, the last thing I've done is I read an A, right? And if I read a B right after, then I'm doomed. And so I think that this does actually work, and it would have probably been the DFA that we would have thought of because, if you're reading Bs, if you're reading any number of Bs, then the only thing you care about is like the parity, and the parity is captured by the row here, right? So I'm going back and forth with the parity, and I'm accepting if I'm in this row because this is for the evens, and I'm rejecting if I'm here, if I end here because this is the odds. So that makes sense. Then at some point I'm going to see an A, right? Once I see an A, I sort of can't go back to this guy because if I see a B right after, then uh I should reject, right? Because I don't want to have AB. So then I'm going to be in this state now, but I still actually care about, yeah, and that makes sense, right? So if I'm here, then I'm odd, and I read an A, then now I'm even. So that's this row. Here, if I'm here, and then I'm even, and I read an A, then I'm odd, right? So this, yeah, this definitely is a DFA that we would have probably thought of um, had we been forced to design it directly. And so instead, this is the DFA that you get from the product construction from these two kind of nice and simple DFAs. And this is once you sort of merge the two dead states together. But yeah, this was just for like an extra exercise, seeing uh, like the difference between the process of just doing this, which is like quite nice, and then actually doing the product construction. Okay, so yeah, that's another video with an exercise.